Greetings, ladies and gentlemen, and this is the Electrostatics review, where I'm going to review all the topics you're going to need to know going forward for your quiz on Friday. And I bring this video to you from my mystery location of where I am at currently for the weekend. If you stick around for the rest of this video, you'll find out where I am at and for what reason. Alright, so we start with elementary charge. And what is elementary charge? We symbolize elementary charge with E, and its value is 1.6 times 10 to the negative 19 coulombs. Alright, so this you can find on the reference table, but what is it exactly? It's the smallest possible charge. So that means when it comes to possible charges, they can only be done in multiples of E, okay? So E here doesn't stand for electrons, it stands for elementary charge. And which types of particles does this value apply to? And that is a proton, which is the P plus, or the electron. That's E minus. Okay, so both of these, protons and electrons, carry this value of 1.6 times 10 to the negative 19 coulombs, and you can only go up in charge by multiples of these particles. So let's say if you want to increase your charge, if the proton carries the smallest possible charge, you can only go up in terms of protons or electrons. So 2 protons, 2 electrons, never part of a particle, like 1.5 or 2.5. Okay. So when you see problems with protons and electrons or elementary charge, you need to look at that number. Then we move on to conservation of charge. When two charged objects come into contact with each other and then separate, what is being exchanged? So when objects change charges, you can never transfer protons. Never protons. Why? Because protons are located in the nucleus. Alright? So if you try to remove a proton from the nucleus, you change the element. Never exchange protons. Alright? So that means the ones that are being exchanged are electrons only. So objects can only change their charge by adding or removing electrons from themselves, okay? Now, how do you know which object becomes more negatively charged or positively charged? So remember, okay, that positive charge means more protons and they lost electrons. Whereas the negative charge, you have more electrons and they gained it. Okay. So for more negatively charged, gained electrons, and positively charged is lost electrons. Okay. And so you could still have 2 positive objects come into contact and exchange electrons, and one would become more negative by gaining electrons. So even though objects could still both be positive, there's still an exchange of electrons where one could gain and one can lose. Okay. Now the electroscope is one of my favorite things. So remember, you have this guy. We got to draw 2 different scenarios here. Now we're going to start with scenario A with a positively charged rod. So that means our rod here is positive, and we have a neutral electroscope, so that means both positives and negatives have to be present. I want you to pay attention here. When you have a positive rod, it's going to attract the negative charges of the electroscope to the top, and the like charges, the positives, get pushed down to the bottom, causing these leaves to diverge. The same thing happens here with a negative rod. It attracts the positives, and the negatives get pushed down here and repel the leaves. And that's it. Now, electrostatic force. This is a calculation-based question. Two protons are separated by a distance of 6.7 millimeters. Calculate the magnitude and direction of electrostatic force between them. Okay, so we start with two protons. Set a certain distance between them. Okay. So we're looking for Fe. K is a constant on the reference table. Q1 and Q2 are the same because they're both protons, and remember the key word, proton, so you have to think about this charge. Now in your quiz, you're going to be asked to calculate these things, and you better include units, especially for K. Alright, so K's units are in the reference table as well. And R is the distance between them. 6.7 times 10 to the negative third, because it's milli. Now we could calculate. And you get that Fe, the magnitude, is 5.13 times 10 to the negative 24th newtons. And now we have to think about direction, and you have to look at the signs of the charge. Now they're both positives, they are like charges, so like charges repel, so they're going to move away from each other. Okay, and that's your direction, away from each other. And so now we move on to the second page, and I'll tell you where I'm at. I am in Atlanta, Georgia. For what reason? Stick around to the end. Alright, so what are the relationships between the electrostatic force and the following variables? So we have to think back and start with looking at our equation. So let's start with distance, r. Distance r is in the denominator, and there's an exponent. And when you're in the denominator, it's inverse relationship. So if you increase the distance, the force decreases. And then there's an exponent there, so it's squared. This is inverse square. This is right here. And then, when we look at the charge on one object, we're talking about this, just one of them. And this is a linear relationship. When you increase one charge, the force increases as well at the same rate. Alright, now let's think about their graphs. Linear graphs look like this. Constant rate. Inverse square graphs look like this. If the charge on object doubles, the charge on the other object triples, and the distance between them doubles, by what factor would the force change? Okay, so object 1 doubles, object 2 triples, and the distance between them doubles. So let's use dummy variables to solve this. We make everything equal to 1 originally, and then we apply our changes. So we're going to make k equal to 1. This is 2, this is 3 over 2 squared. Multiply this out, you get 6 over 4, and this reduces to 3 over 2. So our new force is 3/2 as much strong as the original, okay? Now we move on to the plug and chug stuff and some drawings with electric fields. Here an electron is immersed in an electric field with a magnitude 80 newtons per coulomb. Determine the magnitude and of the electrostatic force. And they tell us we have an electron. So let's plug this in. So we don't know what this is. They give us this. And the electron here has a charge of 1.6 times 10 to the negative 19 coulombs. We plug it into this equation. So it's 80 newtons per coulomb equals F over 1.6 times 10 to the negative 19 coulombs. Plug and chug, and you get that F is equal to 1.28 times 10 to the negative 18 coulombs. That's the answer. Now we're going to go into the drawing part. We have to draw electric field lines for the 4 scenarios. This is A, B, C, and D. So we'll start with A. Positively charged sphere. Remember that positives radiate outward because they radiate happiness and spread it to the world. Okay. B is the negatively charged sphere, and they suck in the happiness of the world because they're so negative, they want to ruin it. And then C is 2 oppositely charged spheres, so we mean positive and a negative together. Remember that positives radiate out, negatives suck in, so they take all the happiness. Positives give it all to the negatives. Okay? So you should draw something like this. And then for D, 2 similarly charged spheres, you could do either positives and negatives. The only difference here is the direction of the arrows. Because like charges repel, they never touch. So you should have empty space in between them. Like that. The same thing happens with negative, you just change the direction of the arrows. And then the last one is about voltage, potential difference, just calculating. So how much work is done to move 2 electrons across the electric field within a 5-volt battery? So all you're going to need to do is use this voltage equals work over charge equation. So our voltage is 5. Work we don't know. And charge is 2 electrons. So 2 times 1.6 times 10 to the negative 19 coulombs, which equals the 3.2 times 10 to the negative 19 coulombs. So we plug it in. Multiply it out, and you get that work is equal to 1.6 times 10 to the negative 18 joules of work. Okay, and that's it. So, why am I in Atlanta, guys? Well, I'm here for a National Science Teacher Conference where I'm here taking workshops and learning about cool new things to become a better science teacher, you know? So I'm over here trying to become a better person at my job for you guys. Hopefully I'll learn some fancy schmancy new tricks. I'm here with some of the other teachers, science teachers here from Massmith. And so I hope this was helpful. Good luck. If you miss out on the quiz, be ready for a much harder quiz, guys. Do not miss this easier version of the quiz. All right, take care.